Hi there, folks. Today we're going to be looking at modeling polynomial functions. Really, we're going to be writing equations of polynomial functions, kind of the idea here, and discovering what kind of polynomial function is. See, unlike when we've done some of these things in the past, like all linear functions pretty much look exactly the same with the, varying slopes and stuff like that, and they're all in the same format, y equals mx plus b, stuff like that. Even quadratics were either in the format of, y equals ax squared plus bx plus c, or our vertex form, the y equals a times x minus h squared plus k. But with polynomial functions, they're kind of all over the place. Some of them are cubed functions, some of them are x to the fourth, and some of them are x to the fifth. So we kind of have to vary our approach a little bit more in terms of determining what kind of polynomial function it is. It's not as specific as some of the other things we've graphed before. So for example, if we look at this first guy, we can kind of tell from the graph that this one is probably um, an x cubed function based on the number of x-intercepts and the fact that they each pass through. I mean, it could be greater than that, but we'll assume for the purposes of this one, this is an x cubed function. And so if we were kind of trying to figure out how to write this by hand, what we would do is we'd kind of write it in factored form first. We'd say, hey, if I have an x-intercept right here of -5, well, then that means I must have the factor x plus 5 as part of this polynomial. Because if I did x plus 5 equals 0 and solved, I'd get x equals a -5, which represents this guy right here. Okay? So then same thing with the next one. If I look at the next one, I've got an x-intercept at -1. Well, that means I must have the factor x plus 1 as part of my polynomial. And then the last x-intercept I have, the 2, well, that means I must have x minus 2 as one of the values for my polynomial, all right? And then the y-intercept, we'll kind of get to that in a moment, but really this is kind of what my polynomial is going to look like, is y equals this. However, we don't want it in this format. We want it in standard form, and we need to see it in standard form because we got to check to see if our y-intercept matches. So to put this in standard form, I just have to multiply this thing out. And again, it doesn't matter what order I multiply this in. I'm going to start with the last two binomials. And you do your distributive property. And I know some of you probably need to see these little curves here in order to multiply this out. So let's see, that's an x squared minus 2x plus 1x minus 2. Okay? And now I combine like terms. And now I multiply the binomial and trinomial. So now I multiply these out. And again, I'll draw the little, see, I distribute the x, and I distribute the 5. So I end up with y equals, looks like an x cubed minus x squared minus 2x plus 5x squared minus 5x minus 10. And I combine some like terms. And of course, because I draw these curves, I've kind of run out of space. So let me make a little space here. Oh, gotta erase these claws. Oh boy, I erased half the problem up here. That's no good. Let me condense these to make a little room. All right, now let's combine like terms. So we get y equals x cubed plus 4x squared minus 7x minus 10. And when I look at this, if I were to plug a 0 in for x, y would equal a -10. See, right here, this is my y-intercept, but that doesn't match what my graph says for the y-intercept, okay? And so what happens on this is I've got to adjust this equation to match my y-intercept. And you might just say, well, let's just add 8 to it. Well, I can't do that because then if I just change that 10 and don't change anything else, then this thing wouldn't end up factoring into this guy, okay? What I need to do is I need to have a greatest common factor that can come out that would turn that -10 into a -2. Essentially, I just have to look at it and say, hey, what would I have to multiply all of these by in order to get the last term to be a -2? And the answer is a 1/5. So like if you kind of imagine a 1/5 on the outside of this guy here, let me erase. So essentially what we want to do, we want to multiply the whole thing. I can't just deal with the last term. If I were to stick a 1/5 on the outside of this guy this whole time, you see what would happen if I were to distribute that? So you would still factor in the thing I started with, but if I were to distribute that, it's going to turn that -10 into a -2. And so that's kind of the idea here is at the end, we multiply this thing out, and then we just adjust based on the y-intercept. We multiply by the whole thing by something to get the correct y-intercept. Let me slap that 1/5 out here. That's it. I distribute, and I get x cubed over 5 cubed plus 4/5 x squared. I guess I should have written that guy as a 1/5. I apologize. 7/5 x minus 2. I don't know why I wrote it that way. Not that it's wrong, but it's a little weird because none of the rest of them are like that. And that's it. Okay? So it's kind of just working backwards from what we're used to. We're used to having the equation given, we find the x-intercepts. And I'll just take the x-intercepts, work back to the factors, and then it's just a matter of multiplying this thing out and then multiplying through by a value that adjusts the y-intercept to what we need. Okay? So if we look at another one, again, same kind of thing. Here's the zeros. In other words, x equals, those are the x-intercepts. So if x equals a -3, it means I would have, I'll leave a little space this time, x plus 3 is one of my factors. If x equals 1, it means I would have x minus 1 as one of my factors. If x equals 5, it means I would have x minus 5 as one of my factors. And now I multiply this thing out. I know I'm going to run out of space, so I'm going to draw on the claw this time. You'll have to draw it yourselves or imagine it in your minds. I'm going to start with the second two. And I only did that because I know you guys prefer to have a binomial out front that you're distributing. So here that's x squared minus 5x minus 1x plus 5. And I combine like terms. And now I get to do more distributing. I distribute the x. X cubed minus 6x squared plus 5x. Distribute the 3 plus 3x squared minus 18x plus 15. And now I combine like terms. Whew, I'm amazing. I'm incredible at this. But now wait a minute, my y-intercept is not right. See, if you can see right here, right now my y-intercept's a 15. But the y-intercept is supposed to be a -60. So I have to ask myself, how do I turn that 15 into a -60? I got to multiply by -4. Okay? See, if I did this guy times -4, now I'm in business. Now it would equal a -60. So that just means, hey, I have a greatest common factor of -4. Let me just tack that on here. So to finish this thing off, just my distributive property. Ready? -4x cubed plus, oh boy, plus 52. Oh, there's that curve getting in my way again. -60. That's a terrible looking 60. Not too bad. All right, the next one is kind of where the wheels fall off. All right. If you are faint of heart, this one's going to get you. All right. This is the same kind of thing we dealt with the other day. When you look at something like this guy, we want a fourth degree polynomial that has zeros, x equals a -1 plus I, and 2 minus the square root of 3, and a y-intercept of 4. The thing about this is just like yesterday, or a couple days ago when we looked at some of these, Remember, the complex answers always come in pairs. Well, the irrational answers always come in pairs also. In other words, if I have the answer that's written, the x equals -1 plus I, it automatically means that I also have -1 minus I as one of my answers. Same thing with the other guy. This automatically means that I have 2 plus root 3 as one of my answers. These things always come in pair because we get this by doing things like the quadratic formula, which has that plus or minus built in. Okay, and so there's a couple ways to approach this. The last time we looked at this, we approached it from the perspective of, okay, if x equals this, I can kind of separate into the two factors, but these are a lot more complicated. Here's what I like to do with these. I like to just say, you know what, this is like plus or minus this, and this is like plus or minus this, right? So I see these two answers. Well, if I kind of split these up, just work backwards. Think about it. When you solve for x, you undo operations, something like that. Well, undo the process of solving for x. Work backwards. Like here, I would add 1 to each side. I'm just working backwards to the factor. See, that's plus 1. And then here, if I had a plus or minus I, that's because I took the square root of a -1. That's how I get I. So if you kind of undo that process, in fact, if I erase this and just say, you know what, that means that I took the square root of a -1 at some point, right? And that's where I got that plus or minus. Well, undo that process, square each side. And this seems really strange because we are used to doing this when we're solving for x. We're kind of undoing solving for x here. So we're undoing the undoing of the operations, which is kind of a little odd. But here I square this guy. That's going to be an x squared plus 2x plus 1. Again, that's x plus 1 times x plus 1. Take it off to the side and do it if you need to. FOIL, distribute, that kind of stuff. Over here, I just get a -1. And then if I add that 1 back over to the other side, here's the trinomial that I get. And so again, the idea here is if you think about this trinomial equal to 0, you would solve this by completing the square or the quadratic formula. So if I undo, and essentially what I just did is I just undid completing the square. If you look at those steps, if you remember what completing the square looks like, okay, that's what I've undone here, all right? And I've worked my way back to the thing that I had that would give me these two answers. I can do the same thing with this guy, so let's try it again. And again, this is a little bit strange because we're used to undoing what's happening to x. Now we're undoing what's happening to the solution to get back to what I had when I tried solving for x. So like here, I bring this 2 back over to the other side. See, instead of getting x by itself, I'm bringing everything back over to where x is. And now I would undo that square root by squaring each side. See, I'm working my way back to the polynomial that gave me this answer. Again, take this off the side. X minus 2 times x minus 2 is x squared minus 4x plus 4. Over here, when I undo this square root, just gives me a 3. And I'll subtract that 3 from each side. So I get x squared minus 4x plus 1 equals 0. So now I know that the two factors of this polynomial were the x squared plus 2x plus 2 and the x squared minus 4x plus 1. Well, I'm not done yet. Those are the two factors for my polynomial. Ready? We got to multiply those out. Oh, I forgot to leave a little space in case I need to tack on a greatest common factor here. But yeah, I just multiply this out. So I distribute the x squared, and this, again, might be tough for some of you because it's a trinomial times a trinomial. It's going to be an x to the fourth minus 4x cubed plus x squared. And that is a cubed, I promise. There we go. That looks more like a 3. Now I distribute the 2x. That gives me a 2x cubed minus 8x squared plus 2x. And now I distribute the 2. That gives me a plus 2x squared minus 8x and a plus 2. Whew, and now I can combine all those like terms. Before I do that, though, is it okay if well, let me go ahead and do that. Let's see, that's going to give me an x to the fourth. Let's see, a negative 2x cubed, a negative 5x squared, and let's see, where's my x's? Come here, x's, negative 6x, and then a plus 2. And you can see that I have the wrong y-intercept. It was supposed to be a negative 4. Right now it's a positive 2, so I need a negative 2 on the outside of this thing. And that's my distributive property. Oh boy, I kind of ran out of space here. Ready? Y equals, just distribute, negative 2x to the fourth plus 4x cubed plus 10x squared plus 12x. And there's that minus 4. Okay? But again, start with the factors, start with the answers you have and work backward to the factors, undo the operations that happened when we were solving for x. And I know this one is probably a little bit more complicated. You're probably staring at this thing going, I don't know what just happened. That's okay. We'll practice these over the next few days here to make sure we got them. And again, these are not the ones that I'm going to be throwing at you constantly. It's going to be more like those first two. So if you hung with me for those first two and maybe you're a little unsure about this one, that's okay for right now, okay? The last piece of this is extra easy because we're going to use the calculator, so make sure you grab your calculators out. So what we're going to do is we're going to identify the degree of the polynomial by looking at common differences. So here we're going to look at a table of values. And when I say a first common difference versus a second common difference, third common difference, fourth common difference, that kind of stuff, I'm just looking at the pattern. I'm looking at the pattern between the values. So like normally when I look at the pattern, I look at and see what am I adding each time to get from one y value to the next, okay? And if on the first try, when I look at one y value to the next, on the first try, if I get the same value being added each time, it means it's a first degree polynomial because I got the common difference on the first try. That's what the common difference is what I'm adding each time, okay? Now, if I look at the polynomial and what I'm adding each time is not the same, well, then I do that process again using the common difference that I just came up with. So I have one round of common differences where I look at what am I adding each time, and then I just look at it again. So I look at the difference between the differences. And if the second round gives me the same number each time, it means I have a second degree polynomial because it's a second common difference. If they're not the same, then I keep going. I look at the differences of the difference of the differences, and I just keep going. And you know, this sounds a little complicated when I describe it here in words, but really, we just look at the values that are written down and say, okay, what do I add to get from one value to the next? Okay, and I keep doing that. I go row after row until I get the same thing being added each time. And however many times it takes me to get the same thing being added each time, that's the degree of the polynomial. And you know, the first degree, we already know that. You know, we know that if the pattern is I'm adding the same thing each time, it's a linear equation. That's a first degree polynomial, okay? But these other guys are to help us identify when we have degrees that are larger than that, okay? If it was a fifth common difference, it would be a fifth degree polynomial, okay? And so on and so forth. So again, that sounds complicated, but it's not. When you see it, you're going to go, oh, okay, that's a lot easier than it was looking like it's going to be, okay? For example, if I take a look at this first one. In this table of values, I just look, how do I get from one value to the next value in the table? So like here, to get from a 5 to a 3, I add a negative 2. So that's the difference between those two. It's not a common difference yet, sorry. To get from 3 to a 1, I add a negative 2. To get from a 1 to a negative 1, I add a negative 2. And to get from negative 1 to negative 3, I add a negative 2. And so that's a common difference because the thing I added was the same each time. and it happened on the first try. So this is a first degree polynomial, all right? So I know it's a first degree, it's a linear equation, and I can write the equation of this thing. I could do this on the calculator if I really want to, but I don't need to. I could come over here and just say, oh, you know what? I could put it in point slope form. Y minus a y value equals m, which is the -2, that's the slope, times x minus an x value. And then I could put this in slope-intercept form if I want to. -2x plus 2, and then add the 5. If I wanted to do this on the calculator, here's what I do. I'm going to start with the TI. So on the TI calculator, we go to our stat menu. I go to edit, and then I type in this table of values. So I punch in the x values into list 1. I'm going to punch those y values in the list 2. And now what I'm going to do is I'm just going to do a regression. Okay, so I go to stat, over to calculate. But now here's the thing, I had to do that whole common difference things by hand because that tells me which regression to do. Because I know this is a first degree polynomial, I know that I can find the equation by doing a linear regression. And I hit enter. On the newer calculators, it'll say, hey, is this in list 1, list in list 2, and you have to go down to calculate. And it'll spit this out. Y equals ax plus b. Notice the a value is -2, the b value is 7. And isn't that what I have written down right now? Y equals -2x plus 7. Y equals ax plus b. Okay, so we can use our calculator to calculate this for us, and that's going to be the idea, behind these other ones. Obviously, this one you could do it by hand because it's linear. All right, but when it's not linear, we want to rely on the calculator. For the Casio folks, it's the same thing. You go to menu, over to stat. You're going to punch your list in. And if you remember doing regressions previously, we've done linear regressions and quadratic regressions. We're just going to expand this a little bit today. Obviously, this one's a linear regression. But remember, Casio folks, you go to calculate, which is F2 right now, and then regression. And then yours is a little bit easier for today's lesson because it's just saying, hey, what degree? Like this is first degree, so find the x with the first degree. See x the first degree, x to the second degree is listen. So I just hit F1 for f to the first degree, and there it is. Y equals ax plus b. It tells me a is a -1, b is a 7, y equals a -2x plus 7. Piece of cake, right? If I look at the next one, check out this next guy. Again, let's look at the difference between the values. Like here, it went up 2, so it's +2. And now this went up 3, so that's +3. And +4, and +5. And you notice that is not the same, so this is not a common difference. So the first row failed, so I move on to the second row. I do the same thing, but I compare the values that I just wrote down in purple, and it's okay. To get from 2 to 3 is +1. To get from 3 to 4 is +1. To get from 4 to 5 is +1. And so you notice those are all the same. That's a second common difference. See, this was the first row. This is the second row. So since the second row, the second common difference was all the same, this is a second degree polynomial. It's an x squared, okay? And so I can go to my calculator again. I go to, I'll do the TI first. I go to stat, edit, and I replace these. Oh, look at that. The x's are already set up, 1, 2, 3, 4, 5. The y's, I just have to change the 2, 4, 7, 11, 16. And again, the calculator doesn't know what degree polynomial this is. That's why I had to do that by hand. So now I go to stat. I go over to calculate. A second degree polynomial would be a quadratic. So I go down to quadratic regression. So quadreg is a quadratic regression. I tell it to calculate. And look at that. Y equals ax squared plus bx plus c. So it spits it out in standard form. Tells me a is 0.5, b is 0.5, and c is a 1. So my equation is y equals 0.5 x squared plus 0.5x plus 1. And that's it. See, the calculator does all the work for me. The Casio folks, same thing. If you hit exit, it'll bring you back to this guy. Let's change that list. Let's see, 2, 4, 7, 11, and 16. And this time, and this is why it's a little bit nicer for the Casio. I don't have to think about the naming of this thing. It's a second degree polynomial, so I'd go to the x squared right there at F3, and beep, boop, beep, it spits it out. A is 0.5, B is 0.5, and C is a 1, which is the same thing I got on the TI calculator. Okay, there it is. All right, but look at the last one here. Let's find the difference. So right here, to get from 3 to 3, I add 0. To get from here to here, I add 2. Get from here to here, I add 10. And to get from here to here, I add 24. Not even close, right? Not the same at all. So let's keep going. To get from here to here, I add 2. To get from here to here, I add 8. And to get from here to here, I add 14. Again, still not close. So I keep going. Run out of colors. To get from here to here, I add 6. To get from here to here, I add 6. Oh my, that's the same thing, which means this is a third degree polynomial. See, this was the first difference. This is the second difference. And this is the third difference. So because the third was the one that was common, that was the same, this is a third degree polynomial. So I go to my calculator, my good buddy calculator, TI first. I go to stat, edit. Oh, that jerk Mr. Jansen changed the x values this time. Let's see, 2, 3, 4, 5, 6. Why couldn't I just leave him as well? Oh man, that Mr. Jansen, he's a real jerk. This one, 3, 3, 5, 15, 39. And now I go to stat, over to calculate. And this is, this is going to be tough because maybe we don't know these names yet, but you might notice the regressions are all in order. Linear regression, linear regression is first degree. Quadratic regression is second degree. Cubic regression is third degree. Quartic is fourth degree. And that's all the calculator has. So you can probably bank on me only giving you ones that are of the fourth degree at the most for calculating these. So this one, cubic regression is what we want because that's the third degree. And go down and tell it to calculate. And notice here, y equals ax cubed plus bx squared plus cx plus d. And it just gives us the coefficients in order. 1, -8, 21, -15. Let's see, it was 1, -8, I believe. Then I want to say it was -21, and then -15. Oh, my memory is the worst. A +21 and the -15. There we go. Plus. Okay. Casio, folks, same thing. Exit out of here. Hit the exit button. Brings you back to this guy. Put these new values in. And I know it's a third degree, so I go to the F4, which is the third degree. And I forget how high this one goes. Yeah, that one, the same thing. It only goes to x to the fourth. Oh, now this is interesting. It did something little squirrely here, and this will happen every once in a while. On this calculator, it'll happen. It'll happen on the TI sometimes as well. But it gave me a little bit of an error in terms of how close it is. When you see 0.9999999, do you know what the calculator meant to say? Hopefully you realize it meant to say a 1. When you see negative 0.7999999, it meant to say a -8. When you see 20.9999, it meant to say a 21. And we say 14.999, it meant to say a 15. And the same thing came up when we were doing some of those left-bound, right-bound guess things and that kind of stuff. It just happens sometimes. The calculator's trying to narrow this thing down, and sometimes it's off by just a hair. You have to kind of take that with a grain of salt and say, okay, it meant this, all right? And notice when we round those properly, we get the same values that are written here. Okay, so again, you just look at the common difference, and I think this is probably one of the easiest things we've done in this unit. Okay, just looking at the difference until you find the one that's in common. However many times it takes, that's the degree of polynomial. And again, we do that by hand because the calculator has no way of knowing that that's a third degree. We have to tell it it's a third degree. Okay.